All right, hi, welcome back from your second break. This is Dr. Matthew J. Traum. This is the third video of the seventh lecture of the Engineering Design course. We are talking about Product Performance Specifications Procedure. It's a four-step process, and we've talked through the first three steps. And now we're on to the final one, which is actually just to do it, to state succinctly and precisely the performance requirements for each attribute. So there's a couple things to keep in mind here. The first is once the attributes list has been compiled. Now, what's the attributes list? Well, that is essentially a customer needs statement that you've developed both from documents and from conversation with the client that state all of the attributes that have to be satisfied for your design solution to be acceptable to the client. So once an attributes list has been compiled, then a performance specification has to be written for each of those attributes. And there is at least a one-to-one correspondence, meaning for every customer need, there has to be at least one specification. Now, sometimes there can be more. One customer need might require two specifications or three specifications, but there has to be at least a one-to-one correspondence. That's how you know that you're meeting all of the customer needs as you've created this set of specifications. So that's the first metric. The second one is to keep in mind that specifications say what the product must do, not what it must be. And we've talked about this before in a couple of slides in this lecture, in that you might find that the client is actually giving you solution-based metrics. They're actually telling you specifically what component or what object they want you to buy or design or whatever it is to meet a particular requirement, and you need to stand your ground and make sure that you don't cave in to specifications that confine the product to be a particular thing. So it's important at this stage to go through and make sure that your specifications say what a product does, not what it is. So that's the second thing. The third is whenever possible, it's important to express performance specifications in quantitative terms. Now remember, the reason for this is because in the next couple stages of the design process, we're actually going to start designing things, and we need a way to evaluate the things that we've designed against one another to essentially down select to the best possible solution, which we then do a detailed design for and some prototyping to start that process. So you need to be quantitative so that you have something that you can compare as you're looking at these different possible solutions. You can actually work out the numbers and say to yourself, yes, this solution actually meets the specifications and this other solution doesn't. So we're going to discard the solution that doesn't, and we're going to hang on to the solution that does. But you can only do that if you have quantitative requirements. So for example, instead of making some sort of vague statement like the device has to be lightweight, you actually want to choose a number. So you should say the maximum weight of the device should be 10 kilograms, for example. The more precise you can be, the less vague, the better, because it actually allows you then to compare and benchmark different solutions against each other to make sure that you're actually meeting the customer needs once they're quantified into specifications. The last thing to keep in mind is whenever possible, you want the specifications to be a range, not a specific value. So a range, again, allows the design engineer to be more flexible and to come up with a wider range of possible viable solutions that still fall within the design requirements. So whenever you can, for example, you should specify not a specific value, but a range of possible values. So I say here as an example, a specification should not say the height of the device is 425 millimeters. If there's a range that's possible that still meets the design requirements, give the range as your specification. So the range, say between 400 and 450 millimeters, is actually a better specification because it allows for design flexibility that still meets the customer needs. Okay, so those are the four steps. What I wanted to spend just a few minutes doing was to describe to you guys a product that I am working on as part of a startup company that I founded, and to show you how I've translated the objectives into my criteria, into my specifications. So what this device is, it's called a velocity profile interrogator. And if you haven't researched me already, my startup company actually makes educational laboratory teaching equipment, and so this is a piece of equipment that would allow a student, particularly a remote learner taking a course online, to actually receive this in a package that's shipped to them through the U.S. Postal Service. They would open the package, they would assemble this experiment, and they would use it to measure velocity profile. So we're actually looking at the shape of the velocity profile in a circular pipe down the length of the pipe. So when I was first conceiving this thing, I came up with a number of objectives, which are shown here. So I want my pipe to produce laminar flow. I want it to measure a laminar velocity profile. I want it to produce turbulent flow. I want it to measure a turbulent velocity profile. I want it to achieve some measure of fully developed flow. And then, of course, as I said, this thing has to be shipped in a box to a remote learner. So it's got to be U.S. Postal Service shippable, and ultimately it has to be affordable. It can't be so expensive that a student can't afford it. So none of those objectives are quantitative in any way, and yet they pretty well define what I want the ultimate iteration, the ultimate product to be, and how I want it to perform. And so what I had to do was take my own list of objectives, my own customer needs that I developed myself, and quantify them and convert them into these criteria, which are my specifications. So we know, by the way, that we're going to use a number 2 Schedule 40 PVC pipe. That is for weight and size purposes, and we're interested again in the flow development down the length of the pipe and measuring the shape of this velocity profile. So knowing that the pipe is a number 2 Schedule 40 pipe, I know its dimensions, and so to produce laminar flow, knowing that I'm using air as the working fluid, I can solve for the velocity, knowing that the Reynolds number has to be less than 2,000 to keep the flow laminar. So this is a quantitative metric that arises from the need for laminar flow. To measure the laminar velocity profile, well, I know this velocity, and I know that that velocity produces a pressure difference in a pedostatic probe. That pressure difference is 1/2 of a Pascal, so that's where that specification comes from. I also want to produce turbulent flow, so the Reynolds number for turbulent flow has to be above 4,000, meaning I'm going to need some sort of variable fan or something here that's going to allow me to get both the low Reynolds numbers and the high Reynolds numbers. But from the high Reynolds numbers, we get this range of possible velocities, with 30 meters per second being as high as I really want to go before the system becomes just unwieldy. So up at 330 meters per second, I end up with a differential manometer pressure of 550 pascals. So I'm going to need to accommodate both this very low pressure for laminar flow and this very high pressure for turbulent flow. I know the development length is about 1.12 meters. So ultimately, this device has to be longer than that to allow the fluid time in its turbulent state to fully develop. It also has to be USPS, that's U.S. Postal Service, shippable. Meaning, if you go to the U.S. Postal Service website, you find that there's a weight requirement, which is less than 70 pounds, and there's a length requirement, which is essentially 108 inches. And so knowing that this pipe is about 3 inches in diameter, the part length has to be less than 2.5 meters. So that's where those specifications come from. And then ultimately, the cost, well, this has to be affordable by students. And so based on my interactions with students and my own experience not too long ago as a student, I set the total price at about $50. So we can't exceed $50 for one of these units for it to be affordable to students. So that's how I converted my objectives into design specifications for a product that I designed and built. Okay, so that is the end of this presentation. Thanks for sticking with me. I realize I'm a little over my 7 minutes. Appreciate your time and attention, and I'll see you in the next video. Thanks. Bye.